This video is about multitasking. So I'm going to show you how we go from one CPU core at the start, running instructions one at a time and only one thread going on, to the point where we can launch tasks that'll run concurrently with other parts of the system. So let's dig into the code and see if I can help you understand. Of course, I need to help myself understand as well. Good old start kernel. This is where we're still running everything in a nice, even sequence. We set up different things in here. No sense in talking through every single instruction here, but let's look at a function that gets us started to do multitasking. Schedule init. Set up the scheduler. Now, this is the task scheduler prior starting any interrupts. Of course, you need interrupts to do multitasking, because how else would a section know that it needs to jump to something else? So we're going to do all this before the interrupts are enabled. Here's schedule init. Notice this part, make us the idle thread. Now, there isn't multitasking going on yet, but we're going to schedule this idle thread. And that idle thread won't actually take place yet. That'll be later on. Schedule clock init is important because this clock is the one that's going to interrupt each task and go on to another task, interrupting it only when the time slice is up. Schedule clock init sets up some simple things, and it also has this comment here that once we mark schedule clock running, schedule clock tick takes over. In other words, that's the thing that keeps track of tasks, this schedule clock tick. After schedule clock init completes, we still have several initialization situations that happen. And finally, what we want to do is get to rest init. Rest init. Now it says something about RCU scheduler starting. This is the read, copy, update, has to do with memory sharing. So we're getting close to sharing between tasks, all in a multitasking environment. Now we say user mode thread kernel init. Wow. Now we've actually launched a separate task called kernel init. Now that we've actually launched kernel init, there are two things going on. That place that started the kernel init is still proceeding down to its end, but in the meantime, this kernel init is going on. So let's see how all that stuff fits together. In addition to that task, we're going to introduce something called asynchronous operation. And this really helps during the boot operation. So there's actually going to be some asynchronous activity going on within this task that we just launched. So let's see if we can prove that by looking at the code. Here's the definition of kernel init, the task. This is our first task that we're launching here. It says wait for completion, and it says K thread. So this is a new thread that's being set up just for this task. Then we do this function called kernel init freeable. Kernel init freeable gets its name because we're doing the initialization functions that can be freed up because they'll never have to run again, only at the very beginning. So let's see if we can find something that's going to help us. I had mentioned earlier that there was asynchronous tasks that can go on. So down here is async init. This sets up the ability to do asynchronous operations. The asynchronous operations are started and we do something called basic setup. Now, in basic setup, we're going to call a function which we should recognize from before. Populate root fs does an important thing. It calls async schedule domain. So here's the workhorse of the uncompressing process, and that's going to be done by this function, but it's going to be done asynchronously. So that takes off and runs separately from the rest of it. So we're inside a task and we're doing these asynchronous operations on top of that. Returning to do basic setup, which called the decompression for the setup of the RAM disk. Now we go down here and notice it says wait for init RAM FS. So it's going to wait. It's doing these other things, but down here, it's not going to go forward until the init RAM FS has completed itself. So we did the async init. We got some of that started. Any other functions that had to happen, those were done concurrently along with the asynchronous process. So that speeds up the boot. Finally, we have console on root FS, so we've actually mounted the root file or the RAM disk, and now we can actually read the console file from there. So that's a big step. Once we return from launching that asynchronous operation, now we wait for async synchronize full. So if there's any other asynchronous operations that happen to be going on, we wait for that to complete. Now we can free up all these different functions that were done during initialization. So we're getting almost to a running state. Notice we come down here and say system state equals system running. So things are looking up for us. Before we lose our place, here's where the kernel init task was launched. Now, after that was launched, we continued to do these operations. So concurrently with all of those things that were going on, including decompressing the init RAM FS file, we're doing all these operations down here concurrently. And slowly we get down here and we do CPU startup entry. CPU startup entry is in, guess what? The idle file. So we're actually getting ready to go into our idle state. So here we go, online idle state, and then we do this function called do idle. Now we're in do idle, which is in a while one loop, which is essentially indefinite, and this keeps checking to see if there's something else that's coming up. So it's just waiting anxiously for another task to interrupt it and keep moving. There you have it. We're up to idle. And now we want to figure out what's going to interrupt the idle task and do more tasks. Another video coming up.